Um, Hello and welcome to Lecture 5 of the course ECE 1B for Spring 2020. The title of the lecture, as you see on the slide, is Byzantine Generals. So before proceeding with the topic of Byzantine generals and the puzzles that lead to it, given that this is halfway through the quarter, let me tell you a little bit about what we have done so far and where we are headed. We are dealing with puzzling problems, which are problems basically of two kinds. They either look deceptively simple, but they turn out to be quite difficult when you look more deeply into them, or just the opposite. They look very difficult at first, or even impossible, but with the appropriate insight, they can be readily tamed. We can find solutions to them. Many engineering problems are puzzle-like, especially in computer engineering. And in this course, each lecture starts with puzzles that we try to solve together. And then after we solve the puzzles and figure out ways, general method for dealing with them, I introduce you to computer engineering problems that are related to those puzzles. So far, we have had 4 lectures previously. Easy, hard, impossible, which basically contain the Collat's conjecture as part of the puzzles. Placement and routing that was introduced through the houses and utilities puzzle. Satisfiability, the puzzles involve making change, making exact change or various ways of making change. Last time we had cryptography, but the puzzles were secret messages. Today we'll talk about Byzantine generals with puzzles that deal with lawyers and truth tellers. And then in the second half of the course, we have 5 other topics, actually 4, given that one of the Mondays where our class is scheduled is Memorial Day. So I will decide whether to eliminate the next to the last one or the last topic to accommodate that holiday. Binary search, puzzles dealing with counterfeit coins. Task scheduling, Sudoku puzzles will lead us into the problem of task scheduling. String matching is related to word search puzzles. Sorting networks, we deal with them after examining puzzles having to do with rearranging trains. And finally, malfunction diagnosis, whose related puzzles have logical reasoning, are of the logical reasoning variety. Okay, so this is basically a short review of what we have done and where we are headed. Okay, so let's start with some simple puzzles. The setting for the puzzles that we will cover early on in this lecture is as follows. You are on an island populated by 2 tribes. Members of one tribe consistently lie. Members of the other tribe always tell the truth. So we call them the truth tellers and liars, the 2 tribes. Tribe members can recognize one another, but you can't tell them apart. So by just looking at a person, you won't be able to tell whether the person is a truth teller or a liar. But the tribe members themselves can recognize each other. Okay, so this is the setting for the puzzles. Okay, here is the first puzzle. These are warm-up puzzles, they're simple kinds. You run into a man on the island and ask him whether he is a truth teller. So you ask this man, are you a truth teller? A blaring siren prevents you from hearing his answer. So you ask the question, are you a truth teller? But you could not hear the answer. Then you ask, sorry, did you say you're a truth teller? And he responds, no, I did not. To which tribe does the man belong? Okay, so you didn't hear the answer to your question, are you a truth teller? So you ask again, sorry, did you say you're a truth teller? And the man responds, no, I did not. To which tribe does the man belong? As usual, please pause the video at points like this where I'll ask you to solve a puzzle and think about it for a while before advancing to the solution that I reveal on the slideshow. Okay, so please attempt this problem, and I'm going to reveal the answer. He's a liar. Okay, well, in puzzles such as this, where you say, okay, is a person a truth teller or a liar? There are just two possible answers: truth teller or liar. Okay, so it's possible to consider both cases and see which one is consistent with the answer that you heard. Okay, can this person be a truth teller? All right, let's examine that. If he were a truth teller, okay, when you ask the first question, he would answer yes. Are you a truth teller? A truth teller would say yes. But you didn't hear that answer. You said, sorry, did you say you are a truth teller? Okay, he did say he's a truth teller, and he's a truth teller, so he will say yes. So the second question, he will respond yes. But he said, no, I did not, so he must be a liar. Which is consistent, because the first question you ask, he would have said yes. Are you a truth teller? He would have said yes, because he's a lawyer. Okay? Then you didn't hear that yes. So did you say you're a truth teller? Yeah, he did say he is a truth teller, but he responds the opposite. Say, no, I did not. Okay? So the lawyer is consistent with the information that we have provided in the puzzle. Okay, you meet a woman on the island. This is a second simple puzzle. What single yes-no question can you ask her to determine whether she is a liar? Okay. In the previous puzzle, you actually asked two questions. Even though you did not hear the first answer, that first answer actually helps you in figuring out the tribe from which this man comes. But now I'm asking you to ask a single yes-no question to determine whether a woman you meet on the island is a liar or a truth teller. Of course, the question can't be, are you a truth teller? Because both kind of people will say yes. And it can't be, are you a liar? Okay, because both type of people, both tribe members, would say no. Truth teller would say no. The liar would say no, I'm not a liar. Okay, so that simple question will not work. So what single yes-no question can you ask this woman to determine whether she is a liar or a truth teller? Okay, again, please pause the video, think about it, and I reveal my answer. There are various ways to answer this question. So here is my solution. If I asked you whether you were a liar, what would your answer be? Okay. If the answer to this question is yes, the person is a liar. The answer to this question is no, the person is a truth teller. Okay? Of course, you can also ask any question whose answer you already know, and assuming that the people on that island also know the answer to that yes no question, then lawyer will give you the wrong answer and a truth teller will give you the correct answer. For example, you can say, are the leaves on that tree green? Suppose there's a tree in sight with green leaves. Are the leaves on that tree green? The truth teller would say yes, and a liar would say no. All right, so that's also another possibility. So let's advance the difficulty level a little bit by now considering two people whom you meet simultaneously on the island. Let's call the two people A and B. A says both of us are from the lawyer's tribe. Which tribe is A from, and what about B? Okay, so here you're not asking any question. A just volunteers this information. Both of us are from the lawyer's tribe. Which tribe is A from, and what about B? Again, think about this for a minute or two. See if you can come up with the answer. And the answer is A is a liar, B is a truth teller. How did I deduce this information from that just one statement the person made? Can both of these be truth tellers? No, because if A were truth tellers, and both of them were truth tellers, A would not say both of us are from the liar's tribe. So that case is ruled out. Can both of them be liars? Well, if A were a liar and both of them were liars, then A would not say both of us are from the liar's tribe because that would be the truth. So that case is also ruled out. So two truth tellers and two liars are ruled out. What about A being a truth teller and B being a liar? Okay, if A is a truth teller, he would not say both of us are from the liar's tribe. Okay, because A is a truth teller. So the only other option that is left is A being a liar and B being a truth teller. Again, because the number of cases is a small finite number, in this case four cases, you can easily analyze all four cases and see which ones are consistent with the information that you have. Now you meet two people, let's call them C and D this time. C says exactly one of us is from the lawyer's tribe. Which tribe is D from? Okay, exactly one of us is from the lawyer's tribe means one of us is a liar and one of us is a truth teller. In other words, both cannot be liars. Okay, which tribe is D from? Again, think about this. I will reveal the answer in a few seconds. D is a liar. Why? Suppose D were a truth teller. Okay, can C be a truth teller? If D is a truth teller, can C be a truth teller? No, can't be, because C is saying exactly one of us is from the liar's tribe, and if both were truth tellers, a truth teller C will not say that. So if D is a truth teller, C must be a liar. Okay, does that make sense? C is saying exactly one of us is from the liar's tribe, but that's the truth in that case. C is a liar, D is a truth teller, so that case also does not make sense. So D must be a liar. Now you meet two people, call them E and F, on the island. E says it is not the case that both of us are from the truth tellers tribe. Which tribe is E from, and what about F? So E, one of these people you meet, maybe a truth teller or a liar, makes this statement: it is not the case that both of us are from the truth teller's tribe. In other words, that one case, truth teller is ruled out, but there are still 3 cases that are consistent with that statement. Which tribe is E from? What about F? Think about this. I will reveal the answer now. E must be a truth teller and F a liar. First of all, this answer is consistent with what E says. E is a truth teller, and he is saying both of us are not truth tellers, which is a correct statement. I leave it up to you to rule out the other 3 cases, show that the other 3 cases are not possible, and therefore this is the only possible answer to this puzzle. Okay, this leads us to question 1 of the 4 questions that you need to answer to report your attendance in this lecture. Remember, you have to send an email with answers to the 4 questions, and make sure you specify that this is attendance report for Monday, let me see, just make sure. Yeah, so this lecture is for Monday, April 27th. And do include your name and perm number in the body, at the top of the body of your email. Without perm numbers, it's very hard for me to find you on the class list, which I've organized by perm number because of the way I report attendance on the web page. Okay, so question 1 is this. You meet 2 people, G and H, on the island. So similar to the puzzles, other puzzles on this slide. Each of the 2 makes a statement. Which tribes are G and H from? So the 2 statements they make are this. G says we are from different tribes, and H says G is from the liar's tribe. So G says we are from different tribes. H says G is from the liar's tribe. Can you tell which tribe G is from and which tribe H is from? So that's question 1 for you. Okay, now let's move on to 3 people, make it a little bit more challenging. So you meet 3 people, A, B, and C, on the island of truth tellers and liars. You ask A, how many among you are truth tellers? You don't hear the answer, so you ask B, what did she just say? So you ask A, how many among you are truth tellers? You don't hear the answer, so you ask a different one, B, what did she just say? She said 1, he replies. So B says that A said 1. One of us is a truth teller. Then C adds, don't believe him, he is lying. So you ask A a question, you don't hear the answer. You ask B what A said, and B says that she said 1. And then C adds this information, don't believe him, don't believe B, in other words. He is lying. What can you say about B's or C's tribe? So now again, there are 3 people. Each of them can be a truth teller or a liar. So there are 8 cases, a little bit more difficult to analyze exhaustively. So we resort to drawing a tree structure to keep track of all the cases. so that we can be sure we don't overlook any possibility. This is called exhaustive search, okay? So A can be a liar or a truth teller, two possibilities. For each of those, B can be a liar or a truth teller, two possibilities for each instance. And for each of the four possibilities there, C can be a liar or truth teller. So at the bottom of this tree, the leaves of this tree, are basically the 8 cases that you need to analyze. So you have to figure out which of these are consistent, which of these 8 are consistent with the information given in the puzzle's statement. Okay, so let's take the rightmost branch. A truth teller, B a truth teller, and C a truth teller. So all 3 are truth teller. Is that situation consistent with what we heard? Okay, if A is a truth teller, then when you say how many among you are truth tellers, the answer would be 3, right? Because in the rightmost branch, there are 3 truth tellers. And the truth teller would say there are 3 truth tellers among us. Then you ask B, who is also a truth teller by assumption, what did she just say? Well, she just said 3. So B will also say she said 3. But B said she said 1, so that branch is not consistent with the information in the puzzle statement. So we can rule out that case in which there are 3 truth tellers from consideration. Similarly, the leftmost branch where there are 3 liars can be ruled out because if there are 3 liars, there are 0 truth tellers among them. So when you ask A, the answer can be any number but 0. Okay? Then you don't hear her answer, so you ask B, what did she just say? Well, B, basically being a liar, can say anything. Maybe A said 1 and B says 2. Oh, sorry. A could not have said 1. Maybe A said 2 and then B says 1. So lies about what A said. Okay? However, that third piece of information, C adds, don't believe him, he is lying. C is saying about B that he's lying. But that's not consistent with C being a liar, okay? If C is a liar, he would not correctly identify B as a liar, okay? So that branch is also, so I've ruled out 2 of the 8 branches so far, okay? I can continue in this way and rule out the branch corresponding to truth teller, liar. Okay? I'll leave it up to you to verify that that branch is also not consistent with the information. I can rule out truth teller, liar. Truth teller, liar, truth teller cannot be ruled out. That's actually consistent. So when you have truth teller, liar, truth teller, there are 2 truth tellers among these. So when you answer A, how many truth tellers? She would say 2. Okay, A being a truth teller would say 2. Then B being a liar responded 1, which is consistent. And then C being a truth teller can correctly say, don't believe him, don't believe B, he is a liar. The truth teller correctly identifies B as a liar. So that branch is consistent, and therefore that's one answer. If you continue in this manner, these 2 are also ruled out. And then this last one, liar, and truth teller, that's also consistent with the information that we have. Therefore, in both of these possibilities. B is a liar and C is a truth teller. So we can correctly identify B's and C's tribe, although we can't be sure about the tribe of A. A can be a liar or A can be a truth teller. Both of those are consistent with the rest of the information. But B or C, which are the subjects of the question and the puzzle, we can identify. B is a liar and C is a truth teller. Okay, here's a simple puzzle. Is it possible to ask the exact same question twice of a truth teller and get two different answers? Superficially, it seems that if you ask the same question and the person is a truth teller, you should get the same answer, right? But it's possible to ask a question. So please think about that. And I won't discuss the answer. I'll leave it up to you to study. Okay. Here is another puzzle that leads to question 2 that you need to answer. A different island has tribes that are truth tellers and naysayers. So truth tellers and naysayers, not truth tellers and liars, okay? You're allowed only yes-no questions. Okay, so on this island, one group of people answer truthfully and the other always answer no. And as before, you can't tell these people apart except by analyzing their answers. How can you tell a truth teller apart from a naysayer? All right, so your answer should specify a process by which you decide whether this person you meet is a truth teller or a naysayer. Okay, and question 3 is also on this slide. It's a little bit more involved. There are 12 politicians from this island. They go to a city hall meeting. So 12 politicians, some of whom can be liars, some of whom can be truth tellers, go to a city hall meeting. The first politician says, "Not a single person in this room tells the truth." Okay, of course, that first politician cannot be a truth teller, right? Because if a truth teller says not a single person in this room tells the truth, that's inconsistent with him being a truth teller. So there's at least one truth teller in the room. So that's sort of the starting hint for you. The second politician says no more than one person in this room tells the truth. No more than means at most one. Okay, so there could be one truth teller or no truth teller according to this piece of information. No more than one. So basically the number of truth tellers is let me see. The number of truth tellers is less than or equal to 1. No more than one person in this room tells the truth. The third politician says no more than 2 people in this room tell the truth, and so on and so forth with the same pattern until the 12th politician says no more than 11 people in this room tell the truth. So those numbers change 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for the last one. What can you say about the composition of this group of politicians? What can you say about which ones are truth tellers, which ones are liars? They're the most information that you can gather from these statements about the politicians' tribal membership. Okay, so that's question 3. Okay, there are many other interesting variations of these kinds of puzzles. So in this puzzle, people do not consistently lie or tell the truth, but they do so selectively. For example, in answer to every other question, or on certain days of the week. Okay, so this puzzle has to do with the latter variation. Inhabitants of another island lie consistently on Tuesdays, Thursdays, and Saturdays, and they tell the truth on other 4 days of the week. So they tell the truth on Mondays, Wednesdays, Fridays, and Sundays. So the yellow boxes are truth-telling days. The orange boxes, Tuesday, Thursday, Saturday, are lying days. You have forgotten what day of the week it is, so you ask a passerby, and he answers Saturday. So you ask, what day of the week is today? He answers Saturday. And what day will it be tomorrow, you inquire. Wednesday, he replies. Can you tell what day it is today? Okay, so you ask two questions. What day is it today? The answer comes Saturday. And what day will it be tomorrow? The answer comes Wednesday. And you know that these people tell the truth on the 4 days, Monday, Wednesday, Friday, Sunday. And they lie on Tuesdays, Thursdays, and Saturdays. Okay, so please think about this for 2-3 minutes. This is a little bit more involved than previous puzzles. And see if you can figure out what day of the week it is today. Whether you can uniquely identify the day. Okay, so please do not advance the video until you have worked on this for a while. And here is my solution. Based on answer 1, today cannot be Monday, Wednesday, Friday, Sunday. It cannot be a truth-telling day, because on truth-telling day, the person would not say Saturday. Or it cannot be Saturday, because Saturday is a lying day, and saying that it is Saturday is the truth. So those 5 days of the week are ruled out by the first answer. So the only candidates at this point are Tuesday and Thursday. But based on that one answer, you can't tell whether today is Tuesday or Thursday. But then when you ask what day will it be tomorrow, today cannot be Tuesday. Because if today is Tuesday, tomorrow is really Wednesday. And on a lying day, which is Tuesday, you wouldn't answer correctly that tomorrow is Wednesday. Therefore, Thursday is, so Tuesday is ruled out, and the answer is Thursday. Today is Thursday. Okay, one more puzzle. This one I'm not going to solve. You're going to be asked to solve this puzzle as your question 4. Somewhere on this island of liars and truth tellers, you find 3 boxes. Each box contains 2 balls. One box has 2 white balls, another one has 2 black balls, and the third has a white ball and a black ball. But you don't know which is which. Okay, you can't see inside the box. The boxes have labels. One label reads 2 whites, another label reads 2 blacks, and the third label reads 1 white and 1 black. However, the person who attached the labels to the boxes was a liar. So the label that says 2 whites cannot be correct. In other words, that box definitely does not contain 2 white balls. It can be 2 black balls, or it can be 1 white and 1 black. Okay? You're allowed to touch only one box, take one ball out, and look at its color. So you choose one of the 3 boxes, open it slightly so that you can't see inside, reach in and draw one of the balls. Okay? Which box should you open, and how would you deduce the correct labeling for the boxes from the color of the one ball that you draw? So you open one of these boxes slightly, reach in, grab one ball, and you look at the color. Okay, that ball can be white or it can be black. In each case, answer the question. Okay, what can you deduce from that white ball or black ball that you drew? And how would you switch the labels so that the labels correctly identify the content of the boxes? So this is question 4 for you to answer. And this is the ultimate level of difficulty in these kinds of puzzle. I'll just introduce the puzzle to you, leave it as a challenge for you to study the puzzle and see if you can come up with an answer. Now you're on an island populated by 3 tribes. Members of one tribe always tell the truth. Members of the second tribe choose to tell the truth or lie completely at random. Members of the third tribe consistently lie. So we have the liars and truth tellers, but also a third tribe, which we call the randoms. The randoms just basically give you a random answer. Can be the truth, can be a lie. And in fact, somewhat surprisingly, dealing with these random people is more difficult than even dealing with liars, okay? Because the liars consistently lie, there's at least some consistency in their answers that can help you figure out, get information from what they say, whereas for randoms, you essentially get no information whatsoever. Tribe members can recognize one another, but you can't tell them apart. Okay? So this is the setting for this puzzle. Now, 3 people from the island, 1 representing each tribe. So we call these person 1, person 2, person 3. One of them is a truth teller, one of them is a liar, one of them is a random. We don't know which is which. How can you identify who is from which tribe? By asking only 3 yes-no questions. Each question must be directed at only one person. You can ask the same person multiple questions. So you just say, P1, answer this yes-no question. Then you go to P2, ask a yes-no question. Maybe you go to P3 or go back to P1 or ask P2 again. So 3 questions you can ask of any one of them. You don't have to ask all 3 questions. It's your choice, okay? But the questions have to be yes-no questions. And from the 3 answers that you get, you should be able to say, for example, P1 is random, P2 is truth teller, P3 is liar. Identify the 3 with respect to their tribe memberships, okay? There are some hints at the bottom of this slide that I let you read if you are inclined to attempt this challenge. It's a pretty difficult puzzle. Okay, so what do these puzzles have to do with practical computer engineering problems? The main problem that we deal with in today's lecture is the Byzantine generals problems. But this related problem, the 2 generals paradox or 2 general problem, is also interesting. So let me start with this one. So this is not our main point in this lecture. The 2 generals paradox. Troops led by 2 generals are camped on the outskirts of an enemy city. That orange blob is in the enemy city. And troops led by General 1 and General 2 are camped outside the city. The generals can only communicate via messengers. Okay, these are Byzantine generals. In those days, there were no cell phones or radio or any other means of communications. They had to send messengers between them to communicate. And the messenger has to travel through enemy territory. There's no way around, let's say. So if General 1 sends a messenger to General 2, that messenger must go through enemy territory. And therefore, the messenger will be subject to capture or delays. Okay, so for example, as the messenger moves through enemy territory, he or she may have to hide for a long time if conditions are not right for advancing without being detected. So it may take an arbitrarily long time for the messenger to get through, or the messenger may not even get through, can get killed or captured. Okay? The two generals have previously agreed on a plan of attack, but they must communicate to set up the attack time. So they know the plan of attack, but they don't know when they will be attacking, whether it will be tomorrow at noon and tomorrow at 6 p.m. Okay? And they have to attack together to have a chance to defeat the enemy. If one general with his troops attacks and the other one does not attack, the outcome is catastrophic. So we want to make sure that both generals attack at the same time, or neither one attacks. They decide not to attack, that's fine too. But if they decide to attack, both of them must attack in order to avoid catastrophe. Okay, so let's say General 1 decides that tomorrow at noon is a good time to attack and wants to let General 2 know about this proposal. So G1 sends a messenger. Let's attack at noon tomorrow, with the message, let's attack at noon tomorrow. And the messenger will not, the General 1 will not attack until he has made sure that G2 has gotten the message and will attack at the same time. But how can General 1 be sure that G2 got the message? There's no way. Once the messenger leaves and goes in the enemy territory, there's no way for General 1 to know whether that messenger got through or got through by noon tomorrow. Okay? So he can't assume that General 2 is on the same page and knows the attack time and will attack at the same time. So what should we do? Well, we can sort of agree that when General 2 receives the message, he sends back an acknowledgement. He sends a messenger to tell General 1, yes, I got your message and it's okay with me, I'll attack at noon tomorrow. But General 2, having sent that messenger, cannot be sure that that messenger got through. And if that messenger did not get through, then General 1 did not receive the acknowledgement. And if General 1 does not receive the acknowledgement, he will not attack. Okay? So General 2's dilemma is that he doesn't know whether the acknowledgement message got through. Okay? So suppose the acknowledgement gets through and G1 receives the acknowledgement. So G1 now knows that G2 is aware of the attack time. But G2 does not know that G1 is aware of the fact that G2 is aware of the attack time. So perhaps we need another acknowledgement for General 1 to let General 2 know that he received the acknowledgement message. But then this process can continue to infinity. Okay, we can never be sure that the two generals are on the same page, and therefore they can attack, knowing that both of them will be attacking. No matter how many times these messengers go back and forth, because the last messenger sent, the general who sent the last messenger, cannot be sure that that messenger got through. Okay, he can't be sure that the other general will be attacking at the same time. So this is the two generals paradox. Now, in computer engineering, we have this problem that is very similar to the two generals paradox. When you go to an ATM to withdraw cash, there are two systems basically. There's the ATM that dispenses the cash that you request, and there's the bank's central computer or database where your balance is reduced accordingly. So you get, say, $40 in cash. The ATM gives you the $40 in cash, and the bank's central computer reduces your account balance by $40. Okay? You want both of these actions to take place, or neither one to take place. Okay? If you get the $40 cash and the reduction of the balance does not occur, then the bank loses $40 because the cash was dispensed, but your account was not updated. Okay, if the reduction of the balance occurs on the G1 side, but the ATM does not dispense cash, you lose money. Your account balance was reduced, but you didn't get any money. Okay, so you want these two sides to come to an agreement, either to basically complete the transaction, which involves dispensing cash and reducing the balance, or just basically abort the transaction. Sometimes when you go to ATM, it says, sorry, I cannot complete your request, or I cannot complete the transaction. That's fine too. You go to a different ATM or do something else. As long as the two sides are consistent, either both actions are executed or neither one is executed, it's okay, it's consistent. But you don't want one to take place and the other not to take place. Okay, now these two devices, ATM and bank central computer, communicate through messages over a network. And that network is not totally reliable. That corresponds to a messenger going through enemy territory being captured. Okay, the message is dropped, doesn't get to the other side. Of course, the probability is fairly small in modern day networks for a message not to get through. So basically, we resort to acknowledgments. The ATM sends to the bank central computer a request saying that this guy wants to withdraw $40. The bank central computer acknowledges that it got the message, and the ATM can dispense the cash. However, the acknowledgement message may be dropped. So again, you have to do basically an infinite number of acknowledgements to be reasonably sure that this consistent action takes place. Of course, from an engineering perspective, once you have 2 or 3 acknowledgements, the probability of the two sides not being on the same page, it gets so small that the bank really doesn't mind losing $40 with a very small probability. Okay? Even a bank customer may not mind losing $40 if the probability is 1 in a million, if it's very small. Okay? But the bank definitely doesn't mind losing $40 in the course of providing service to customers. Okay, so this was sort of an entry into the Byzantine generals problem. So because we have unreliable communication, we need these acknowledgement messages. It's pretty common to have acknowledgement messages when we communicate. Now, consider a computer network with nodes. The yellow circles are nodes or computers. The lines connecting them are links. So these are sites communicating with one another to reach an agreement. For example, to select a coordinating or leader site. Okay, typically in distributed systems, one of the sites is declared the leader that directs, the actions of the other sites. And all the sites must come to an agreement, to a consistent opinion about which side should be elected the leader. Okay, now in the course of these communications, sites and links can fail. Sites can fail because computers can crash. Okay, Links can fail because they can get disconnected, or some other thing can go wrong physically with the link so that information cannot be sent over them. Okay, the site status can be healthy. Okay, a site is working. This is the normal case. The site is healthy, it's working well, it gives appropriate responses to every message that it receives. This is like truth tellers, the truth teller tribe. Okay, a site is healthy, tells the truth whenever you ask it a question. A site can be crashed in such a way that it does not respond to any message. This is a quiet site, okay? You keep asking it question, it's crashed. It never responds to a question. This is a quiet site. It can be permanently failed and in a way that it responds identically to every message. This is the analog of naysayers in the tribe situation. So whatever you ask this site, because it's failed, maybe it gives you the response corresponding to 0, which is no, okay, instead of occasionally answering 1. So this is a naysayer site. It can be permanently failed in such a way that it gives you the wrong response. This is the analog of the liar tribe. So there's a site, whenever you ask it a question, you ask what time it is, well, it's failed. The clock on that site is showing the wrong time, so it gives you the wrong answer. It can be arbitrarily failed, may give an unpredictable response. So sometimes it gives you the correct response, sometimes it gives you the wrong response. Sometimes transient failures are like this. There's a failure that occurs once in a while, but it's not permanent. So sometimes it gives you the correct response, sometimes it gives you the wrong response. This is the analog of the randoms tribe. And finally, it can be maliciously failed. It gives a response that is calculated to do the maximum harm to whatever mission you are trying to accomplish. The site basically is an adversary to your goals, and it's a worst case failure scenario. This is what happens when a site is hacked and is taken over by hackers. So hackers are controlling that site, and when you communicate with that site, the hacker calculates to see, how to respond to a query in order to do maximum damage to your mission, to your goals. And this is known as Byzantine failure. Now, as you go down this list, roughly speaking, it gets harder and harder to deal. Of course, the first one is not a failure, truth teller. The site is working perfectly. But all the others are failures that get gradually harder to deal with. So if a site is quiet, never answers, at least it never misleads you. Okay, you don't get an answer to your question. If it's a naysayer, it gives you a consistent no response. And after a few questions, you sort of can guess that something is wrong. Okay, a liar is at least consistent in the lies that it tells. So it may be possible to deduce some useful information from a sequence of lies. A random is pretty difficult to deal with because you have no idea whether the answer is true or false. And a Byzantine answer, Byzantine failure, is the worst of all these failure types. Okay, so Byzantine generals, basically, the problem of Byzantine generals deals with this kind of Byzantine failures. Okay, so let me formulate the problem. The Byzantine generals problem. This is an abstract problem that has counterpart in actual communication problems that we try to solve in computer systems. So there are 3 generals camped outside enemy territory. There is a commanding general G and 2 lieutenant generals L1 and L2. And again, they have to communicate through messengers, and the messengers have to go through enemy territory to get to their destination. There's no way around it. This is just by assumption, okay? And then they have to communicate in such a way that all 3 are on the same page, and therefore they all attack or none of them attacks. We don't want 1 or 2 to attack and 2 or 1 to not attack, okay? They won't have enough force to defeat the enemy if that happens. So we want all 3 to be on the same page, attack or not attack. Now we throw a monkey wrench in this process and say that one of these 3 generals can be a traitor. The commanding general or one of the 2 lieutenants can be a traitor, and therefore in the communications that traitor can try to mess up the decision process so that the consistent decision is not reached by the other 2 loyal generals. Of course, the traitor we can ignore that, the traitor cannot be on the same page with the other 2. But at least the other 2 we want to make the same decision, attack or not attack. Okay, so how do we analyze this problem? The problem is non-trivial, even if the messengers are totally reliable. In other words, the messengers are guaranteed to get through, okay? So even if we have, in the context of computer engineering, we have perfectly reliable communication. If one of the 3 sites that they're trying to reach an agreement has a Byzantine failure, is a traitor, then the other 2 will not be able to reach a consistent decision. Okay, so let's see why. It's a very interesting analysis. So let's say the commanding general says attack, sends the attack command, and Lieutenant 2, one of the 2 lieutenants is a traitor. Okay, so Lieutenant 1 receives the attack command, but he can't trust that command because it's possible that the commanding general is a traitor and is trying to mess things up. So he has to verify that command in some way. And one way to verify a command is to just basically get information from the other lieutenant. So in this case, the commanding general is loyal, and he sent an consistent attack command to both lieutenants. Lieutenant 1 got the attack command. Lieutenant 2 got the attack command. But because he's a traitor, he says to Lieutenant 1 that he said retreat. Now Lieutenant 1 is sitting there. He got an attack command and a retreat opinion, which is a relay of the commanding general's command. He can't be sure here. Is the commanding general loyal so that the attack command is genuine and he should attack? Or is the commanding general a traitor, which is this case? So if the commanding general is a traitor, he might say attack to one lieutenant and retreat to the other lieutenant. And then Lieutenant 1 receives that relay of information that L2, being loyal, says the commanding general told me to retreat. So in these 2 cases, Lieutenant 1 cannot distinguish between these 2 cases, because in both cases he's receiving an attack command from the commanding general and is receiving a retreat opinion from the other lieutenant. There's no way this lieutenant can tell which of these 2 cases is in play. In this case, he should attack. In this case, he should not attack. Okay, because the commanding general is a traitor. Okay, so it turns out that with 3 generals, this problem is unsolvable. There's no way to orchestrate these communications so that the 2 loyal generals reach a consistent decision. Notice that when there are 2 good generals and 1 traitor, a majority of the generals are loyal, but that majority in this case is not enough. It's not enough for a majority of the generals to be loyal in order to reach a consistent decision. So what's the solution? Well, if you have 4 generals, the problem is solved. You can have 1 traitor and still be able to reach consistent decisions between the 3 loyal generals. So let's take the 2 cases where the commanding general is loyal. So he would give the same command. A loyal general will give consistent command. So for example, it says attack to all 3 lieutenant generals. Then these lieutenant generals exchange information among themselves. Lieutenant 2 says to Lieutenant 1, he said attack. This traitor can say anything to Lieutenant 2, and he can say anything to Lieutenant 1. So that question mark means he can say attack or retreat. But notice what L1 receives. L1 receives attack, attack, and possible retreat. So a majority of the opinions that L1 receives are correct, and he can make the decision based on that majority. L2 receives attack, attack, and a possible retreat here. Again, L2 makes the correct decision, and therefore these 3 generals will all attack, will reach a consistent decision, despite the fact that there was 1 traitor among the 4 generals. If the commanding general is a traitor, then he may send basically garbage, arbitrary commands, ABC to the 3 generals. Then they exchange information among themselves. Lieutenant 1 receives A, B, and C. Lieutenant 2 receives A, B, and C. Lieutenant 3 receives A, B, and C. So whatever decision process these lieutenant generals follow, they will reach the same decision because they all get the same data, A, B, and C. So whatever the decision process we implement for them, they will all reach the same consistent decision, attack or retreat or whatever other options there are. Okay? So in both cases, when there's just 1 traitor, whether it is the commanding general or it is one of the lieutenant generals, the loyal generals will reach consistent decisions. Okay, so this can be generalized. If there are F Byzantine failures, you need at least 3 F plus 1 nodes to reach agreement. So with 1 traitor, with 1 Byzantine failure, you need 4 nodes, 4 generals. If there are 2, if it's possible to have 2 traitors or 2 Byzantine failures, you need 7. Okay, if there are 3 traitors, you need 10 nodes at least to be able to implement a valid consensus or agreement protocol. So here's an example, 2 Byzantine failures or 2 traitor generals, and there are 7 altogether, so that should be enough to reach a consistent agreement, an agreement between the green nodes, which are the good nodes. Okay, so I'm going to skip this. There's this link. There's a very interesting article that you can read if you want, but you're not required to do that. Okay, so without malicious or Byzantine failures, majority voting is always enough to reach a decision. So for example, in this case, there are 7 nodes that are giving you yes-no decisions or answers. There are 4 yeses and 3 nos, and this fuser basically takes the majority of the input opinions, and it gives you the majority opinion is more likely to be correct than the minority opinion. Okay, sometimes the opinion are not yes-no answers, but they're numeric values, such as temperature measurements, let's say. So there are, let's say, 7 sensors in a particular environment that measure the temperature of a particular device or particular point that you want to have an accurate temperature for. So you provide 7 sensors in case some of them fail. You want to be able to determine the correct temperature. Okay, so these are the readings, let's say, of the sensors, 78.2, 45.5. They're quite varied, but you may notice that all these numbers are pretty, so, sensor readings are typically approximate. So even if these are pretty good sensors, they will not read the same value. But 78.2, 78.7, 77.6, they're in the same ballpark, in the same vicinity. There are 2 outliers here, 120 and 45.5. So you may say, okay, let me remove those outliers. They're likely fails, 3 of them, 21.2, 120, and 40. The other 4 are in the same ballpark. So you can either average them and say, okay, this average is likely to be the accurate temperature. So you average those numbers to get 78.4. Or you don't remove outliers. You just take the median of the numbers. A nice thing about median, when you take averages, the outliers affect the average and give you a bad value. So if one of these outliers was 1,000, for example, and if you average, that 1,000 would affect the average adversely. But if you take the median, essentially the extremes are taken out of play, and the median of all those values will be 78.2, which is pretty close to the mean. Okay, in fact, this kind of scoring is done in some athletic events. For example, in gymnastics, a bunch of referees give scores to various players, and there are different procedures, but in one procedure, the highest score and the lowest score are removed because there may be this expectation that, one of the referees who happens to be from the same country as an athlete may be, biased and give a higher than fair score. And a referee who may be from a country that is sort of an enemy of the player's country, or they may be at war or whatever, can give an unreasonably low score. So by removing the highest and the lowest scores, you basically protect against those kind of biases. Okay, the same thing applies if I ask several people what time it is. I can take the majority opinion if a majority exists, or a plurality opinion if it exists, or I can take the median of all the values, and so on. The mean of all the values. Okay, there is an interesting, voting is used in many contexts. Mathematicians have studied it because of the kinds of problems that we have been discussing, decision-making process. Political scientists have been studying because we use voting in political elections. Sociologists have been studying it, what they call social choice. So, for example, if you're holding a party and trying to decide what kind of drinks to serve, you may sort of conduct a poll, ask different attendees what drinks they would prefer, and then choose the drink served according to the preferences. So this is a social choice. And economists have been studying it too, because in economics, again, these kinds of making decisions based on imperfect information is a major topic. It turns out you can prove mathematically that no voting scheme is totally foolproof. Okay, no matter what voting scheme you choose, no matter how complicated, it's always possible to construct an example to defeat that voting scheme and basically force it to make inappropriate or wrong decisions. Okay, so for example, if you have a regular voting and there are two candidates, A1 and A2, who are pretty close to each other in their views and policies, and there's candidate B, who is completely different, and if you vote among these three, then A1 and A2 may split the votes, and B can get a plurality of the vote and be elected. Sometimes we have runoff elections, so if B gets most votes, and let's say A2 gets more votes than A1, then a runoff will be held between B and A2, and during the runoff, the people who originally voted for A1 may go and vote for A2, so that problem basically disappears, but still, even runoffs do not solve all problems. There's a voting scheme called approval voting, where a voter basically does not vote for just one candidate among the three, but says which of the candidates he or she approves of. So some voters would say I approve of A1 and A2. Some voters will say I approve of B. So A1 and A2 will get their fair share of the votes because it's possible for a voter to vote for both of those, approve both of them. So this is less problematic. Vote splitting does not occur because a voter can approve more than one candidate. But there are other problems. So as I said, theoretically it's impossible to devise a perfect voting scheme. No matter how complicated you make it, there's always an example that you can construct to defeat that process. And finally, the voting scheme that comes closest to perfect, it's not perfect, but comes closest, is the so-called border voting. In border voting, each voter does not vote for one or approve a set of voters, but rank orders the candidates. So for example, one voter can say, I prefer A1 over A2 and A2 over B. Another voter can say, I prefer B over A2 and A2 over A1, and so on. So each voter rank orders the three options or four options, however many candidates there are, and then each first place choice gets n minus 1 point. Second place, n points, sorry. The second place choice gets one fewer points. And the last place choice gets 1 point. And then we tally the points. So if A1 is the first choice of many voters, he or she will get a lot of points because each first choice gets n points. But it's possible for a candidate to be first choice of quite a few people. But for A2 to prevail because he or she was the first choice of a few people, but also the second choice of a lot of people, and the second choice actually gets, quite a few points. So it's possible to win without being the first choice of a large number of voters. So this comes closest to being the perfect voting scheme. But even this one is not perfect. Okay, so I'm going to skip this last slide. And if you're interested, please read it. There's an interesting observation here that if messages are signed, in other words, if messages cannot be forged, in other words, if a general tells you to attack with a signed message, then you have to forward that signed message. You cannot construct a fake message with the correct signature. Okay, therefore you have to relay the correct message. You can't change it. With signed messages, then agreement becomes easy. If you can't fake a message, agreement becomes easy. All right, that's it for this lecture. Bye for now until the next lecture.